Hello students, I am Kirti Bhosale, currently working as Assistant Professor in N.V. Navle Sinhagad College of Engineering, Solapur in Department of Civil Engineering. I have experience of 21 years which includes 10 years in industry and 11 years in teaching field. I have done my ME in structures and currently I am pursuing PhD in structural engineering. So our today's topic is analysis of portal frame by flexibility method. As you can see in question diagram, AB is column part and BC is beam part, A is fixed support and C is hinge support, and the loading is 50 kN point load at point D and 25 kN per meter UDL on a span of 3 meter. So we have to analyze this portal frame by flexibility method. So we will go to step 1. Step 1 is to find DSI and select redundant. So you know, for fixed support we have 3 unknown support reactions and at hinge support 2 unknown support reactions. So DSI is total 5 support reactions minus 3 available equilibrium equations, therefore total DSI is 2. Okay, as DSI is 2, we have to select 2 redundants, R1 and R2. So I will select R1 as BC downward and R2 as HC towards right. You can select any direction or any sense. Okay. Now we will go to second step, that is generation of DRD matrix. DRD matrix is nothing but it is displacement due to external load. So this we have to refer this loading diagram for DRD matrix. So I will now divide this beam in 3 parts: BC, part BC, part BC, part BD and part DA. Okay, remember that we have removed redundants. So R1, R2, once we have removed, this C support or C point becomes free end. Okay, so we have divided in 3 parts this portal frame, and now we have to refer this table. We will tabulate all the moments in this table. Okay, so first row is member, which we have divided CB, BD and DA, and the origin will be C, B and D for each part, and 0 to 3, 0 to 2 and 0 to 2 are the integration limits. Okay, what is this M? M is, capital M is bending moment due to external load, that is bending moment equation, capital M. Okay, and then small m1 is moment equation due to unit R1, and m2 is moment equation due to unit R2. Okay, now we will again go to this loading diagram for generation of DRD matrix. Okay, so as we have discussed, that is we have divided into this frame into 3 parts. Then I will take section 1 in first part CB. Okay, so this is section 1 and I will write down bending moment equation at this section. So I will consider all the forces on right hand side of the section. As you can see, the only UDL is acting on right hand side of the section. So this bend UDL is causing clockwise movement to the right side of the section. Therefore, clockwise movement to the right of the section is hogging, which is minus. What will be the moment of this or magnitude of this moment? W into x into x by 2, that is W x square by 2. W is 25. So you can see in this table that for this part bending moment value is written over there as minus 25 into x by 2, that is minus 25 x square by 2. Okay, so part CB is over. Then we will go to second part BD. Again, now I will take section 2 in part BD. Again, considering right hand side of the section, this UDL is acting. So moment of this UDL to the right of the section, again hogging, that is minus 25, that is W, into L, which is 3, into L by 2. So W L square by 2, and which is hogging, therefore minus. So again table. So it is bending moment equation is minus 25 into 3 into 3 by 2, which is minus 112.5. Okay, then we will go to the third part and take section 3 in part DA. Again consider right hand side of the section. Again this UDL is causing minus 112.5 bending moment as in the already discussed part for BD. Okay, and now the additional load is 50 kilonewton point load, and this is again causing right clockwise moment, again hogging. Therefore the moment, this 50 kilonewton load will cause moment of magnitude W into X, that is minus 50 into X. Okay, so now here it is written minus 112.5 minus 50x. Okay, so this row is completed, and then we'll go to the next part, that is unit due to unit R1 and due to unit R2. Okay, so this is the loading diagram for generating flexibility matrix. Okay, now we have to consider only one action at one time. Okay, let me explain first that this loading diagram, that here there will be no external load and only unit action will be there. Unit redundant action is there. What is flexibility? It is displacement due to unit action, that is here unit redundant, and here no external loads will be placed. Okay, please note it. And then again take section 1 take section 1 in CB part, again considering right hand side force, that is R1. Remember here R2 is absent. Okay, so this R1 is causing again right clockwise moment minus 1 into X, so minus X, you can see it in the table, minus 1 into X. Then go to second part, that is part BD. Take section 2 again this R1 is causing right clockwise moment minus R1 into this perpendicular distance is 3 meter, so minus 1 into 3. Yes, in table you can see minus 1 into 3, that is minus 3. Okay, then go to third part, take section 3 in part DA. Again this R1 is causing right clockwise moment minus 1 into 3. Okay, so again in table you can see minus 3. Okay, so M1 is over, that is second row is clear to all of you. Then go to third row, that is M2 moment equation due to unit R2. So now we have to apply only R2 here, and remember R1 is now not present. Okay, so again take section 1 in part CB, and this R2 is causing 0 moment about section 1. Okay, so in table you can see M2 is 0 for first part. Then go to second part, take section 2. Again this R2 is causing right clockwise moment minus 1 into perpendicular distance X, so minus 1 into X, you can see here minus X. Then take third part and take section 3 in part DA. Again this R2 is causing right clockwise movement -1 into this perpendicular distance. What is this perpendicular distance? This is 2 meter plus this is x. Okay, so -1 into 2 plus x. Yes, you can see it in table. -1 into x plus 2. Okay, so now this table is clear to all of you. Okay, then we will actually get the values of DRD matrix and F matrix. First we will discuss DRD matrix. So for DRD matrix, first element is DRD 1, and which is integration 0 to L capital M into small m1, capital M into small m1. Okay, so put the respective values as in the table. From the table you can get all the values. Yes, okay, and these values I have taken from for first part, for second part, and for third part. M into m1 divided by EI into dx. Okay, so you can always simplify this integration by putting the proper integration limits, and you will get value of DRD 1. Okay, then on similar parts go to DRD 2. What is this DRD 2 value? Is capital M into M2. Okay, now again put the respective values from the table and get value of DRD 2. Now in this way we have already derived DRD matrix. Okay, 1 by EI, and these are the two figures. Okay, now we will go to step 3, which is generation of flexibility matrix. Now we will have, as ds size 2, flexibility matrix will be square matrix of order 2. Means we have to derive 4 elements. First is F11, and which is M1 into M1, and you have to take these values from the referred table. Okay, so for these 3 parts, and again solving these 3 integrations, you will arrive at this value F11. Okay, then again F12 will be M1 into M2. Okay, of course integration 0 to L divided by EI dx. Again putting the all values from the table and solving for integration, you will arrive at this value. Okay, now on the similar lines you can get value of F22 as M2. Yes, as M2 into M2. Okay, and on the similar lines you will arrive at this value of F22. Yes, in the last step F1 value of F12 and F21 will be same. Okay, now we have derived the flexibility matrix. Okay, flexibility matrix we have arrived at these values. Okay, now we will go to next step, that is step 4. We have to use the flexibility equation. What is flexibility equation? It is DRD plus F into R, that is unknown matrix, is equal to 0, because in this case dr is 0 because no sinking or rotation of support in this example. So by solving these two simultaneous equation in matrix form, you will get this value, first value as R1, which is Vc, and it is coming minus. Remember, you have assumed it as downward and the value is negative, means actually it is positive, and that is upward. Okay, and R2 we are getting, that is HC. We have assumed HC towards right, but it is minus, therefore actually it is towards left. Okay, so now in this step we have found out both the extra unknowns, that is both the redundants. Okay, then step 5 is to calculate support reactions. Then as you know, once we have got the values of different redundants, then you can always find out support reactions by using the equilibrium equation. First, summation ma equal to 0 and you will get ma value. Then summation fy equal to 0, you will get value of va. Summation fx equal to 0, you will get value of ha. Now you are ready with all the support reactions. Okay, now go to step 6, which is to draw the bending moment diagram. Okay, first we will see this is the free body diagram. Free body diagram is nothing but the diagram which is showing all the external loads plus all the support reactions which we have already calculated in subsequent steps. Okay, and remember, while drawing bending moment diagram, we have to follow these two arrows. Okay, means while drawing bending moment diagram of BD, we will refer this direction, and while drawing bending moment diagram for BC, we will follow this direction. Okay, and of course sagging positive, hogging negative. Okay, so this is the free body diagram. Then go to the next point, that is while drawing bending moment diagram, first you have to draw the reference lines, okay, of frames. Then you have to plot the support moments, that is ma hogging, therefore outside the frame. Okay, again mb hogging, therefore outside the frame, mb hogging outside the frame, and mc is 0, therefore it is at that position. Okay, so join these points and you will get bending moment diagram due to only support moments. Okay, clear to all? Then on this support moment diagram, you have to superimpose moments due to external loads. So how? So just see here. Okay, so first we have already drawn support moments. Okay, and now we are going to superimpose on these values the bending moments due to external load. So on part BC, UDL was acting, therefore bending moment diagram due to UDL will be parabola and with the ordinate W L square by 8, and it is sagging, therefore plus. Okay, and here for in column part AB, the central point load was acting, therefore the bending moment diagram for central point load is triangular and with this ordinate. What is this ordinate? PL by 4. Okay, it is, this is value is due to central point load. Again it is sagging, therefore plus. Okay, so sagging we can say. Okay, so your final bending moment diagram is this, which is excluding the overlapping part. Okay, so this is the final bending moment diagram, and here you can say that we have analyzed fully the given portal frame with the help of or by the means of using flexibility method. Okay, thank you.